Another type of rational equation word problem we can classify as a distance problem. Took this problem from page 573 in your textbook. If you want to follow along or refer back to that for any questions you might have. But what we have here is we have Sandra is rowing a canoe on Stanhope Lake. Her rate in still water is 6 miles per hour. It takes Sandra 3 hours to travel 10 miles round trip. Assuming Sandra rowed at a constant rate of speed, determine the rate of the current. So one thing that we need to keep in mind here is although it does say that she is traveling in still water at 6 miles per hour, that doesn't necessarily mean that's how fast she's going at any given time. With these distance problems, there's always force is either helping you or hindering you in your speed. So in this case, our force is current. So if we're rowing against current, we're going to go slower than 6 miles per hour. Whereas if we are rowing with the current, we're actually going to be traveling faster than 6 miles per hour. With any distance problem, the big equation that you want to keep in mind is distance equals rate times time. So in other words, the distance you travel will be how fast you go times how long you've been going for. Now with distance problems, you might not always use this equation in this form. In this particular equation, we're actually going to divide both sides by r. So we end up getting time equals distance over rate. Now, in other problems, you might want to divide by t, and you can get r equals distance over time. So that might be helpful in another problem. But for this particular problem, we're going to use this equation here. We're going to use this equation because we were given that her total time was 3 hours. So if we're going to start to build our equation, we know that the total time t was 3 hours. Now that 3 hours is composed of working with the current and working against current. So Sandra is traveling a round trip, meaning that she's going to go out and then come back in. So if we assume that going out she's going with the current and coming back she's going against the current, if we add up those two times, that should give us our 3 hours. So now that we should have an understanding of what we're trying to solve and the problem as a whole, we're going to try and come up with expressions for both Sandra's time with the current and against the current. So if we use this equation we have in the top right, with the current, her time is going to be the distance she traveled, which if she is going 10 miles in a round trip, going out would be 5 miles. Now our denominator is going to be her rate. So her rate is going to be, in still water, she is traveling 6 miles per hour. And since she's going with the current, she is going to be adding however many miles per hour that current is traveling. So her entire rate would be her 6 miles that she's paddling on her own in still water, plus whatever she's getting pushed along by the current. So if we come back up to our equation, our time is 5 over 6 plus r. Now if we think about her time coming back, and again we're going to refer back to this equation, that the time is always going to be distance over rate. So her distance coming back is still 5 miles. Her rate in this case, she's paddling 6 miles per hour, but she's going against the current, so it's working against her. So it would be 6 minus r. So 5 over 6 minus r. So now we have this equation for us that we can solve. Now before we move on, I do want to talk about the rates when we're working with current or wind speed or things like that. So if you come across another problem where, say, you're given the current speed and maybe we're trying to find Sandra's speed in still water, the problem might set up a little bit different. So something that you should probably put in your notes is your rate is always going to be your rate. So in this case, 6. She's traveling 6 miles per hour. But if we don't know that rate, then that would be our variable. And then plus or minus nature rate, which in this case was current, but it could be wind speed, as I said, or other forces of nature, things like that. But it's always going to be your rate first, plus or minus nature's rate. It's not going to make a big deal when you're working with current or you're working with wind, but when you're going against current or against the wind speed, it's very important that you have your rate first minus nature's rate. So back to our problem, we're going to get common denominators and then multiply through. So my common denominator here would be 6 plus r, 6 minus r. So I'd multiply this first fraction by 6 minus r over 6 minus r. I know that doesn't really look like an r. I'm going to multiply the second fraction by 6 plus r over 6 plus r. My final fraction, 6 plus r, 6 minus r over 6 plus r, 6 minus r. Now that we all have the same common denominators, what we can do is we can multiply both sides by 6 plus r, 6 minus r. When we do that, that would end up simplifying the denominator. Now, some teachers, some videos, they might just tell you cancel out the bottom. Just know we're multiplying both sides by that common denominator. So that's what's going to simplify it out. I don't really have a lot of room in this workspace, so I'm not going to show that out, but know that there is mathematical principles behind that you're multiplying the left side and the right side of the equation by 6 plus r, 6 minus r. Either way, I'm left with 5 times 6 minus r plus 5 times 6 plus r equals 3 times 6 plus r, 6 minus r. So if we remember polynomial equations, if we're going to multiply this right side through, I probably would FOIL that part out first, which would give me 36 minus r squared. Then we still have a 3. On the right side, we can use our distributive property to get 30 minus 5r plus 30 plus 5r. If I clean up the left side, I'm going to have 60. The 5r's would end up simplifying out. And if I distribute this 3, I'm left with 108 minus 3r squared. So I'm left with a quadratic equation. Now, we should know to solve quadratic equations, we want to set it equal to 0, and then try and factor or use the quadratic formula. I'm noticing, though, that the leading coefficient for my r squared term is negative. So because of that, I'm going to add 3r squared to both sides and subtract 108. Some people might subtract the 60, multiply by -1, whatever really floats your boat. Alright, so I'm going to add 3r squared to both sides. Oops, let's go to the pen. So we have 3r squared. I'm going to subtract 108 on both sides. Now if I subtract 108, I'm left with minus 48. And now we want to factor. So it looks like I have a GCF of 3. Okay. And if I take out a GCF of 3, getting sort of ahead of myself here, I'd be left with r squared minus 16. I can take that even further to be 3 times r minus 4 r plus 4 equals 0. So I end up getting answers of r equals plus or minus 4. Now, this is a real world problem, meaning it has context to it. So if r in this case stands for current speed, we can't have negative current speed. So what we have here is our current speed is positive 4 miles per hour. Now, what we do want to make sure is that's not an extraneous solution. So we want to just plug that back into our original equation, make sure that it all works out. So I'd plug in 4 for my current rate. What we end up getting is 5 over 10, which is 1/2, and 5 over 2, which if we add 5 over 2 to 1/2, we get 6/2, which is 3. Everything checks out.